Hi there, my fellow mainframers and computer performance analysts. We are regularly consulted by customers who are considering a processor upgrade or a change. A common question that we are regularly asked is, why is it that a specific machine could vary in delivered processor capacity? Or another way of asking it is why is it that a given machine will deliver more or less capacity from one workload to another, or from one customer to another, or even due to a configuration change? During this video, I will discuss the three primary factors that affect processor capacity. Hi everyone, my name is Peter Enrico of Enterprise Performance Strategy. My team and I are here to help you get great workload performance while optimizing the usage of system resources in the mainframe environment. Our education and our Pivotor software are geared towards helping you get better performance results and faster. We created the Mainframe Performance channel to teach you how to do what we do. Now, if you're new here, click that subscribe button, and any of the references I give in this video, I'll be sure to link in the references below. Okay, you bought a new processor. Why is it that this specific machine delivers more processor capacity at certain times of the day than other times of the day? Or why is it that this machine delivers more capacity for your batch workload than, say, your online workload? Also, why is it that a certain configuration option in place causes the capacity of the machine to change? Another is, why is it that you could have the same exact machine type and model as another company, but that other company gets more capacity out of the machine than you do? Wouldn't you think that delivered capacity for a machine would be constant? Well, there is a lot of background information that is needed to fully answer these questions. But during this video, I will discuss at a high level the three primary influencing factors that influence a machine's capacity. I will work to put out additional videos to discuss each of these in greater detail, but for now, I'm going to go through the three primary influencing factors of processor capacity. Okay, the first processor capacity influencing factor is something we call instruction complexity. Instruction complexity is something that changes from one processor family to another. What is instruction complexity? At its core, instruction complexity refers to the processor's architecture. This includes things like the speeds of the CPUs, the types of instructions available on the machine, the sequence in which the instructions are executed, the way they interact with the processor design. Examples of instruction complexity include things like the cycle time of the CPUs, how the instructions are wired to execute. Other examples are the CPU architecture for the instruction, things like pipelining and branch prediction and out-of-order execution, and many, many other architectural functions and features. For example, here is a table where I am showing a list of delivered capacities for IBM's one-way 701 models of IBM's mainframe machine types. On the very left, we see listed the generation of the machine. We then see the common name of the machine, the year the machine was made available, and actually the machine type. We even see the gigahertz of the CPU for the machine. The configuration of each machine listed here when tested is exactly the same, but notice the PCI column. The PCI column you see is IBM's viewpoint of the processor's capacity. PCI stands for Processor Capacity Index. In reality, PCI is the term that IBM uses instead of MIPS, which is millions of instructions per second. Now, as you can see in this table, it shows that for each 701 processor, it delivers more and more processor capacity itself, or PCI capacity, and more MSU capacity with each successive generation of the machine. This is due to the instruction complexity. Take special note of the last two machines listed. They both even have the same speed CPU, but they deliver different amounts of capacity due to the architecture of the machine. This is a great deal of, and a great deal of this is actually due to the instruction complexity, which is the architecture of the machine. So just the machine architecture, the instruction complexity, influences the capacity delivered by a machine. The second processor capacity influencing factor is what we call path length. Path length refers to the code path executed by a customer's applications and transactions. We think of this as the sequence of instructions. The actual path lengths executed by an application workload will always vary based on several factors such as what a particular transaction requires. For example, the code path length of, let's say, a financial transaction may change depending upon the individual customer's interaction. Or we can have two banks. Each of these banks has a deposit money transaction. Because each bank has their own application code, one bank's deposit money transaction may require a longer path length than, let's say, a similar transaction by another bank's application code. So the path length would be different. Because of this, the path length can change from one customer to another customer, and even from one workload to another workload. And you can imagine the processor's effort and efficiencies to execute those path lengths may vary. Code efficiencies matter, and this is why you need to encourage your developers to code efficiently, to select the appropriate coding language, to use the best compiler options, and to pay close attention to the application design, and to select the best database manager and transaction manager to run the workloads. Path length efficiencies are key to helping a processor deliver more and more capacity, or to at least influence a processor's capacity. So the second, path length. Now, the third processor influencing factor is the usage of the memory hierarchy of the machine. And for me, this is the most interesting area of study. And why? Because you, as the performance analyst, have little control over the other two factors just discussed. Instruction complexity, as an example, is in near total control of the hardware vendors. It is difficult, and it is also difficult for you to control the path lengths by your developers. And trust me, your developers are not going to continually recode applications to suit a specific machine or architecture or generation of a machine. But when it comes to the usage of the memory hierarchies, there are a great many things that you can do to positively or negatively influence the processor's delivered capacity. Okay. Now first, when I refer to the usage of the memory hierarchy, what I'm referring to is the usage of the processor caches and the memory by the systems and the workloads. You see, in the world of processor caches, distance matters. Now here is a pictorial diagram of an IBM mainframe processor containing multiple CPUs and chips and nodes. And what I want to point out here is that there are various levels of processor caches. In the IBM mainframe, these caches are known as L1, L2, L3, L4, and memory. And as you can imagine, as code is executing on the CPUs, those CPUs are constantly reaching for the next instruction or the next piece of data in the L1 cache. And you can imagine then is that the L1 cache, by the way, is right next to the CPU. But you can imagine that if there is an L1 cache miss, then the CPU has to spend cycles resolving those misses, and those are cycles to resolve the misses increases the further and further away from the processor that the processor needs to reach to get the piece of data. So in other words, a miss that is resolved from memory is so much more expensive than a miss resolved from, say, the L3 cache. And in this area of study, you need to understand that the CPU cycles are being used for one of two primary reasons. And this is an important point. The first usage of the CPU cycles is to do productive work. And that is, CPU cycles are going to be used to do and execute your code for your applications and your workload. And this is a very good usage of CPU cycles. However, the second reason CPU cycles are consumed is to resolve these cache misses. And it is important to understand that the more cycles that are spent resolving the cache misses, the lower the effective capacity of the processor will be. Effectively, you will be driving the capacity of the processor downward as more and more cycles are diverted from doing productive work to resolving the cache misses. Okay? Now, I don't have time to go into this last point in any great detail in this video, but for now, please know that the usage of the memory hierarchy is heavily influenced by key factors resulting in potentially wide variations of realized capacity. And you should understand that as a performance analyst, you will not have much control over construction complexity. And you won't have a great amount of control over path length to affect the processor's capacity. However, you will find, and I will show you, that there are many things you can do to influence the usage of the memory hierarchy to realize greater capacity out of your processor, right? So the better usage of the memory hierarchy, the more delivered capacity you can get out of your machine. So I will make this a subject of future videos. This was meant to be an introduction to the influencing factors of processor capacity. So that's it from me, Peter and Rico. Until next time, work hard at your performance. And again, if you've not done so already, please subscribe to this channel because I'm going to be coming out with more videos on this subject, other subjects related to mainframe performance, mainframe analysis, and mainframe tuning. So enjoy the day, and thank you for spending time with me.